today we're going to discuss 3 problems for University Physics, Chapter 17. Let's get started. 17.65. A carpenter builds an exterior house wall with a layer of wood 3 cm thick on the outside and a layer of styrofoam insulation 2.2 cm thick on the inside wall surface. The wood has a K equals 0.08 and the styrofoam has a K equals 0.01 watts per meter Kelvin. The interior surface temperature is 19 degrees Celsius and the exterior surface temperature is negative 10 degrees Celsius. What is the temperature at the plane where the wood meets the styrofoam, and what is the rate of heat flow per square meter through this wall? So here's the diagram, and here are the respective temperatures and distances. So we can assume that obviously the temperature at the plane where the styrofoam meets the wood is the same, so we can assume that the heat rate from the styrofoam to the center is the same as the heat rate from the middle to the outside. So here's what I just said in equation form, and we can just substitute the values or the variables that we need. So that'll be the constant K times area times the hot temperature minus the temperature in the middle over the length. Or in the case of the wood, it's temperature minus the cold temperature over the length of the wood. So we can just simplify the equation by multiplying L1 and L2, and we'll get this equation. So we can just plug in the values, and we'll get the temperature of 267.37 Kelvin or negative 5.78 degrees Celsius. And to get the heat flow per square meter, sorry, that's not included. We'll go back to that later. 17.77. You propose a new temperature scale with the temperatures given in degrees M. You define the 0 degrees M to be the normal melting point of mercury and 100 degrees M to be the normal boiling point of mercury. What is the normal boiling point of water in degrees M? A. Temperature change of 10 degrees M corresponds to how many C? So we can solve this just the way we find the conversion rate of Fahrenheit to degrees Celsius by making it a linear graph function. So we set degrees M as y and degrees C as x. So we know the formula for slope is this. So we can just substitute the values with the corresponding melting point and boiling point in degrees C. So we'll just plug that in and we'll get an M equals 0.2528. And next we'll plug that in the point slope formula with a corresponding point, and we'll get the final formula to be degrees M equals 0.2528 degrees C plus 9.8172. And so we'll just plug in 100 to get the degrees M equivalent of the boiling point of water, and we'll get the degrees M equals 35.10 degrees M. And to get the change when M increases by 10, we can just substitute 10 since we know the value of C for when M equals 0. So we'll just substitute that. C equals 0.7231, and we can just deduct the values to get the change in degrees C. So we'll get 39.6 degrees C. And finally, the last problem, 17.101, is a copper calorimeter can with mass 0.446 kilograms contains 0.95 kilograms of ice. The system is initially at 0 degrees Celsius. A. If 0.35 kilograms of steam at 100 degrees Celsius and 1 atm pressure is added to the can, what is the final temperature of the calorimeter can and its contents? At the final temperature, how many kilograms of ice are there, how many of liquid water, and how many of liquid steam? So in this setup, we can say that the total heat will remain in the system, therefore summation of Q equals 0. So right now we'll just sum up all the energies in the system. So that's the energy of the copper can once it increases in temperature, the latent heat of fusion of ice once it melts, and the change in the energy to change its temperature once it's melted, and the energy of steam once it condenses, it'll be negative since it releases energy, and the change of once it changes once it cools down, and they'll all be equal to 0. So next we can substitute the masses and the initial temperatures and the latent heats of fusion, latent heats of vaporization, and the specific heats, so that we can be left with the final temperature. So we can just isolate T to get this equation, and you can just plug that into the calculator to get the final temperature, which will be 86.1 degrees Celsius. It doesn't matter to convert to Kelvin because the change is the same regardless of whether it's Celsius or Kelvin. So to answer the second question, atomic final temperature, there will be no steam or ice left since they are at the freezing point and boiling point respectively. You'll just be left with 0.13 kilograms of water. So going back to the second part of 17.65, we can calculate the energy per unit time per area by simply multiplying the K times hotter temperature minus the temperature in the middle over the length. This is using the styrofoam heat transfer, and you can just simply substitute the values and get 11 watts per square meter. Thank you for watching. I hope you learned something.